So today we're going to talk about typical reference frames and some mission analysis terms. And that should be helpful because this sort of establishes some important things. One of the most important things related to satellite attitude dynamics is reference frames. It's one of the most fundamental things for studying attitude motion. So throughout this class, we're going to be talking about using different reference frames, often several reference frames at once. So you need to become familiar and comfortable with the basic concept. So let's just dive in. I gave sort of a preview last time, but we'll say some more now. So let's talk about what a reference frame is. I'm going to mean by a reference frame a set of three orthonormal unit vectors that define a right-handed frame, a right-handed system. So what do we mean by that? What do we mean by that? If you look at the screen with me, right, a right-handed frame is one that obeys, if you've got two unit vectors, let's call them, let's say, well, let me give some typical notation. I'll just write it here. Typical notation. You've probably seen I, J, and K. And the thing that makes this right-handed coordinate system is that K, the third one, right, equals I cross J. That's the cross product, right? So we've got I cross J is K. And it's right-handed because you use the right-hand rule. If this is I and this is J, then if I use my right hand, I, and then I turn in the direction of J, my thumb is pointing in the direction of K. So it's a right-handed system. And we will always use right-handed system. It's a convention that's developed from early time. And so everything's based on there being right-handed coordinates. It's not like it's a fundamental rule of the universe. It's just a human convention because most of us happen to be right-handed, I think. That's so. Other notations would be, capital IJK. Some other things that you might see are, and we'll use them a lot in this book, is putting numbers. So like E1, E2, and E3, where for this to be a right-handed coordinate system, E1 cross E2 equals E3. So if you define, the nice thing about a right-handed coordinate system is if you define two of the unit vectors, then you get the third one for free because it comes from this right-handed relationship. So if, I don't have a little label on this, but if this was E1 and this was E2, and E1 cross E2, my thumb is pointing in E3. We'll often use N for an inertial frame, or a frame in which you can use Newton's laws. That's why N. And then also B for a body fixed frame. Okay. So that's the type of notation that we'll be using. Right-handed frame. Ortho up here means they are orthogonal to each other. They're 90 degrees away from each other. Normal means they're all unit vectors, so that's kind of redundant. So they specify directions. And a common thing we'll do is there'll be an inertial frame, and then here's my fancy satellite. It's a block of styrofoam. And here's another frame. So if I have a right-handed frame, let's call this the B frame, B because it's blue. And how do I specify how this B frame is oriented with respect to an inertial frame or some frame that I care about? Maybe this is something I'm rendezvousing with. All right. So some typical frames that we use for spacecraft control. There are some typical frames. Satellite dynamics and control. There is what's called the ECI, Earth-centered inertial. So that is, well, I'm going to talk about each of these. Next one is ECEF. Earth-centered, Earth-fixed. How do I write Earth? Earth is a weird word. Earth-centered, Earth-fixed. That means it's fixed with respect to the ground. So like I am right now at rest with respect to the Earth-centered, Earth-fixed. If I was at rest with respect to Earth-centered inertial, I'd be flying that way. Okay, so this is Earth-fixed. That means it's a body-fixed frame attached to the Earth as it's rotating around. So this is a rotating frame. It's one we know and love. There's also what's called the orbital frame. So this is, in some sense, as we'll discuss, it's Earth-centered, but orbit-based. And it is rotating as well because it's moving around with a point in an orbit around the Earth. And then, of course, attached to the body is a body-fixed frame. So I'll just say body or body-fixed. Let's call it spacecraft fixed. You have to get used to this terminology of the word fixed. It just means attached to. Rotating. This is also rotating because the spacecraft could be rotating. Okay, so let's say a little bit more about these frames. The Earth-centered inertial. What is that? It's also called celestial coordinates, which sounds very kind of mystical. So I have a picture of the Earth. Very happy about it. Ah, there, finally, Earth. It's kind of a see-through Earth. If you look carefully, Australia is poking through the other side, so it's like a transparent Earth, but it's the nicest little figure of Earth that I could find. So this is the Earth. Sure it is, Dr. Ross. All right, and so there's a frame. I'll use orange, I guess. And we've got often capital IJK are used. So here's I, here's J, here's K. You could think of this as it's centered at the center of the Earth, but it gives inertial directions. The I-axis is in the direction of the vernal equinox. That is, so if you don't know what the vernal equinox, it's some day in March, typically. And it's when the orbital plane of the Earth, also called the ecliptic, intersects the equatorial plane. So this sort of gives the idea, you have the ecliptic plane, right? And you've got, so the ecliptic plane is the orbital plane of the Earth. And as the Earth goes around the sun, here I'm gonna, if you look at where I am, right? You've got the equatorial plane is actually this plane that's fixed in space. So it has a fixed orientation. And there are 2 times when the Earth intersects, when those 2 planes intersect. One is the vernal equinox, or we call it like the spring equinox in the northern hemisphere. The southern hemisphere, it's autumn, but most of us live in the northern hemisphere. So northern hemisphere, on that day, when these 2 intersect, the direction, the vector pointing from the sun, from the Earth to the sun, is the vernal equinox. So this is a fixed direction relative to the distant stars. All right, this is an inertial direction. So that's one of the directions. And it's a good one. So this is in the vernal equinox direction. The direction of the sun on whatever that day is in March. I forget what it is this year. It's usually like the 21st to the 22nd. And it's a particular time. All right, so it's an inertially fixed direction. The k-axis is the rotation axis of the Earth. So that one is easier. I guess we could say the North Pole, right? It's the real North Pole. It's the rotation axis of the Earth. Okay. And then the j-axis completes the right-handed coordinate system. So it completes the triad of unit vectors. And it's going to be in the equatorial plane. Completes the right-handed coordinate system, or the triad. I'll sometimes refer to a triad of vectors, and that's what I mean. So what does that mean? So I cross j equals k. You would also, you could say, j equals k cross I. That's also true, right? Do the right hand rule. J, no, sorry, k cross I, and my thumb is pointing in the j direction. So these 2 are sort of like the given ones, because we know the rotation axis of the Earth. So as the Earth is going around the sun, right, as it's going around the sun, this direction is a constant direction as it's spinning. That's a constant direction. The vernal equinox is another constant inertially fixed direction. And J just provides it's going to be in the equatorial plane, and it'll complete the right-handed system. So these are the celestial coordinates. They are inertially fixed. And you might say, well, hold on. The Earth's going around the sun and sun's going around a galaxy. Forget about that. It's good enough. All right, so that's convenient for doing the celestial mechanics of, things going around the Earth. But for most satellite missions, you need to know something about where is your satellite with respect to the ground and points on the ground, latitude and longitude points. And of course, the Earth itself is rotating with respect to this Earth-centered inertial frame. All right. So that's where we come to the next frame, which is the Earth-centered, Earth-fixed. All right. So the next one would be the Earth-centered, Earth-fixed, right? So this becomes pretty important. This is a frame that rotates with respect to the ECI frame. So it's a frame attached to the rotating Earth. Capital, or I don't know if Earth should be, I guess it's capitalized, right? We'll capitalize it. And if I insert, I could figure out how to do that. It's my handy dandy Earth. I'll draw what I had before of the Earth-centered inertial frame. And we'll draw this one in. Gosh, what's a good color to contrast it? I don't know. Green? Yeah. Black? Blue? Yeah, I'm fretting about things that are not important here. All right, so it rotates with respect to the Earth-centered inertial. WRT with respect to the Earth-centered inertial. So we'll call this I prime, J prime, and it'll be in the same direction up here, K prime. So K prime equals K, because that's our rotation axis. Right, that's the Earth's rotation axis. And technically, we could even write what is the angular velocity vector, right? As the Earth, here's my globe. The Earth is spinning. And we'll get into this more about how you define the angular velocity, but think of it right now. Using your right hand, you look in the direction, your fingers curl in the direction that a body is rotating, in this case, the Earth. Your thumb will point in the direction of that axis. So it's the North Pole. So that's the direction of the axis of rotation. And if we wanted to write the angular velocity of the Earth, this is omega as a vector, and the Earth symbol is this ancient circle with a cross in it. So this is going to be, a vector, omega vector equals the angular velocity value times the rotation axis, which is K or K prime, because they're the same direction. And what is this? Omega is 2 pi. We write angular velocities in terms of radians. So it's 2 pi radians per sidereal day. Sidereal means with respect to the fixed stars. Okay, so the Earth it rotates 1 full revolution per day. Okay, more or less. All right, so you might be wondering, well, what's the I direction and or I prime and J prime? They're just I prime and J prime. All right, I mean, usually we've got coordinates that are attached to this frame that we're very comfortable with. Sometimes they're called GPS coordinates, but right, latitude and longitude. So latitude and longitude are attached to this frame. And it's complicated because, unfortunately, this is moving. Latitude and longitude are actually moving, all right? So, we'll say more as that becomes necessary. Just think of it as there is this frame, and it's important because satellites need to point at certain spots on the Earth. So the next frame that we'll mention is an orbital frame. And I think I may have messed up here. I said something like it's Earth-centered orbit. I don't know what that means, but let's say something about the orbital frame. Get my handy dandy Earth. Okay, Earth. There you are, dude. Maybe I'll move Earth over here. Now I'll just leave Earth there. Let's leave Earth alone. All right, so the orbital frame, so it actually has its origin at the Spacecraft center of mass. I guess I should draw a spacecraft. It's not going to be an amazing spacecraft. Here's my spacecraft. It's a box, just like this. Here's my spacecraft, moving around the Earth. So the orbital frame is, of course, related to an orbit. So let's give this thing an orbit. Okay, here is an orbit, and I'll have it go. It goes behind, and then it goes this way. That's a pretty good orbit, actually. Kind of proud of myself. All right, so this is the orbit. And the way that the orbital frame is defined, you hopefully learned in astromechanics about the angular velocity vector for an orbit, right? So from the center of the Earth to the spacecraft, that's a vector, the angular momentum of the orbit is r cross, it's in the direction of r cross v, right? So and it's a constant vector. It's an inertially fixed vector. So r cross v, I guess the way I drew this, it's not exactly clear. Let's just say we have our h vector here. So the angular momentum of the orbit, this is perpendicular to the orbital plane. Of the spacecraft. And the O2 axis is opposite of that. O2 axis is opposite h, the angular momentum of the orbit. Okay, so here's the O2 axis. All right, sorry about that. O3 points in the nadir direction. Okay, so O1 axis is in the negative r direction, or nadir direction. The nadir, something is like its lowest point. So the direction pointing at the center of the Earth. Okay, and then O1 completes the right-handed coordinate system. So O1 would be O2 cross O3 completes the right-handed coordinate system. And okay, this is where if we had a circular orbit, it'd be pointing in the direction of the velocity. But many orbits are not circular, so that's not generally true. So if the orbit is circular, O1 is in direction of V, instantaneous spacecraft velocity, inertial velocity. Okay. So there is a question, why choose a vector that's opposite the angular momentum? I honestly don't know, except that it has this nice feature that for circular orbits, O1 is in the direction we're going. One of the unit vectors is in the direction pointing at the center of the Earth, which is going to be important, right? Because this kind of intersection point with the surface of the Earth is going to define our ground track. And so you need something for the last one. It's a convention. It could be one of these, you know, why is everything right-handed? Because 90% of us are right-handed. So there's a convention there. And maybe it's, you know, in the early days of the space age, they just chose this. So this is it, this is what we're stuck with. All right. So that's an important frame. Another frame would be, oh, I guess we could say something about how this frame, it's a rotating frame, right? Because as a spacecraft goes around, there's looking at me, as a spacecraft goes around, let me get a frame here. Ooh, that's kind of nice. Right, so here's my spacecraft. And if I choose this correctly, okay, I've got, it's going this way towards you. So this would be O1, O2 kind of pointing that way, and then O3 is pointing towards the Earth. And of course, as I go around in my orbit, this frame is rotating with respect to the Earth-centered inertial, and usually with respect to the Earth-centered Earth-fixed, except if I'm in geosynchronous orbit, and then those two are locked. But that's just a special case, so don't think of that one. All right, so this is a rotating frame. I don't want to write that in orange. Well, maybe. This is a rotating frame. Since all directions change, well, I guess except for O2. So it's a rotating frame with respect to the Earth-centered inertial. All right. And you can even, like we did for the Earth-centered Earth-fixed, the one attached to the ground, we could give an angular velocity for this. The angular velocity is typically going to change with time for an eccentric orbit. And it'll be in the direction of negative O2. So it'll be some scalar in the direction of negative O2. So we've got a time varying angular velocity of this frame for eccentric orbits. For circular orbits, this will not be time varying. Maybe we'll write that as just, it doesn't have time dependence. So the angular velocity of the orbit will actually be, you can calculate it. So this is for circular orbits. And the angular velocity, there's this thing called the gravitational parameter, but it's the, it's the mass, it's the gravitational constant. If you have an eccentric orbit, the angular velocity of this frame, right? Think of it as, okay, this thing, as it moves around in its orbit, this is going to be rotating. If we're in a circular orbit, this will be steady rotation. If it's an eccentric orbit, there's times when it'll be rotating faster than other times. That's what I mean by time varying. But for circular orbits, this is g times mass of the Earth, r to the cubed, square root of all that. And first, this is going to be roughly like 90 minutes for low Earth orbit, Leo. Well, that's not going to be. T equals 2 pi over omega will be about 90 minutes. Okay. So that's the orbital frame. So it's a frame moving around, but it's not attached to the satellite. There's another frame attached to the satellite called the body fixed frame. So there's this frame attached to the body, and you might have the satellite doing something where it rotates with respect to this orbital frame, right? Because maybe you want certain antenna or other instruments to point at certain parts of the Earth. And when we mean certain parts of the Earth, we mean the Earth-centered, Earth-fixed frame. So there is another frame. Oops. Okay, so there's the spacecraft or body fixed frame. This is a frame attached to the spacecraft. And this is often written, typically denoted by B unit vectors. So if I draw my handy dandy satellite as a box thing, these are directions that are attached to the different faces. So let's call this, say, B1, B2, B3. All right, and so far there's no meaning to these except that they're just some convenient choice of vectors to attach to your body. So here I have a cube, so maybe I'd pick my unit vectors to point perpendicular to the three faces of the cube. And this is just something convenient, okay? But of course, this is not going to be exactly aligned with the orbital frame, because the orbital frame is rotating. Maybe I don't want this to rotate. Maybe I want to be pointing at something, some distant thing out in space, like the Hubble Space Telescope. Or maybe I do want to point at certain parts of the Earth. So I'm going to try to set it up so that this body fixed frame actually rotates at the same rate as the orbital frame, so that they're in line with each other. So I'm going to say that this is arbitrary. It's arbitrarily fixed in the spacecraft, but it is fixed in the spacecraft. And may as well just bring up the Earth. The Earth. And there's Earth. Maybe I'm on some super inclined orbit. So this is the maybe the orbital frame would be like, here's O2, and then pointing towards the center of the Earth would be like O3. And then completing this right-handed coordinate system is O1. Okay. So typically, the body fixed frame rotates with respect to the orbital frame. So you probably noticed now that we've talked about 4 different frames. So that's why appreciation of frames is going to be important. And the relative orientation of the body fixed frame, because the instruments on the spacecraft will typically be fixed with respect to the satellite-based frame. Maybe I need to draw a little like antenna on here, or satellite dish, to emphasize it. Okay, this might need to be pointed in certain directions. All right. So that is that. Okay. We will definitely be saying much more about frames and attitude determination later, right? I guess that's a little bit of a preview, right? You'll have, if you want to know the orientation of the satellite, that's basically saying, what's the orientation of this B frame that's attached to the satellite? And to find that out, there are ways where you can find out where's the direction of the center of the Earth and where's the direction of the sun. And if I have those 2 vectors, that gets me a good way towards knowing my orientation. And why do I need to know my orientation? I need to know my orientation. That's sort of the essence of the spacecraft attitude, dynamics, and control. I need to know it so that I could point instruments in the right direction, point communication apparatuses in the correct direction. I need to have solar panels. So here's another spacecraft. I need my solar panels oriented so that their surface area gets the most sunlight. So I need them, pointing towards the sun. And maybe I have certain other instruments that I want to keep cool, so in the shade. So that depends on what the customer wants. The customer could be NASA. The customer could be some other company. All right. So now we're going to do some mission analysis definition of terms. This will mostly be related to geometry. Okay. So there is I'll bring up my handy dandy Earth again. There's the Earth. Here is a spacecraft. And here's the center of the Earth. If I draw a line from the center of the Earth to the spacecraft, that's going to intersect the ground at some point. Let's pick here. So this point is called the sub-satellite point. Sub-satellite point, or SSP. This is the point on the Earth's surface, because often we care about the Earth's surface. Point on the Earth's surface on line between center of the Earth and the spacecraft. The spacecraft will also have the direction in which it can view things is important. Whoa, I don't know what just happened. That was not intended. So the spacecraft can see, up in the sky, can see the sub-satellite point and some region around it. So that region that it can see around it also has a name. It's called the instantaneous access area. I don't know why they don't call it the instantaneous viewing area, but it's the instantaneous access area. So we can view that as a cone. Maybe I'll try to use a slightly different color here. Right, what can the satellite see? It can see basically some circle on the Earth, and that's the instantaneous access area. Or we'll write IAA. This is the region on Earth around the SSP that the satellite can, quote, see. All right. And it's going to be a function of, the size of that area is going to be a function of the altitude of the spacecraft. The actual part of the Earth you're seeing is going to be a function of where that sub-satellite point is in terms of latitude and longitude. And that's that. Sometimes people refer to the horizon. The horizon would be the edge. Right? Maybe I'll do this in kind of yellow. Wow, that's kind of hard to see. It's not doing anything else. No, that's going to be terrible. Okay, orange. Okay, so the horizon is the edge of the instantaneous access area. There's also this term called the swath width, which is the width of the angular or linear distance from one side of the IAA to the other. So it's kind of the size. It's different. So swath width. But sometimes you just care about the angle that you could view. We're talking about solid angle. There's the cone. There's a question: is this cone tangent to the surface of the Earth? We'll get into the geometry later, but the answer is yes. Yeah, this is the angular or linear distance across the instantaneous access area. So, for this, I might say from here to here is the swath width. So using my globe, well, let me use a tiny spacecraft. Here's a tiny spacecraft, right? If you're really close to the Earth, you can now imagine drawing a cone, and there's only so much of the Earth I can see. You might even ask yourself, well, what's the maximum amount of the Earth I could see? Going back. The maximum amount of the Earth that you could see is half the Earth, right? If you're super far away, you could see half the Earth. If you're really close, you can't see very much. Although just imagine yourself standing up outside you have an instantaneous access area, typically, especially if you're in someplace really flat, you can see pretty far. So your swath width might be, 20 miles. Okay, so let's say some more about this related to the spacecraft geometry. This thing called the SSP, right, the sub-satellite point. As the satellite moves in orbit around the Earth, how's the sub-satellite point moves, its intersection, right? The trace of it during an orbit is called the ground track. So let me show an example of a ground track, and then describe. Here we go. So I think this is an actual ground track for some actual thing. Forget what it is. It was like the first component of the space station. So it's not the current space station orbit, but this is, it's a spacecraft ground track. What's the ground track? This is the path of the sub-satellite point. On Earth's surface. So this is what they show in movies, and everyone's always confused, like, why is it curvy? Because it is. You want the name? Zarya? I think it was a Russian thing, Zarya. But this one in particular, this example this is for a spacecraft with an altitude of, I think it's 500 kilometers and an inclination. Why is the ground track, let's say it starts here, start, it goes that way. And then after going around the Earth's surface once, why doesn't it come back onto itself? What's going on here? Does anybody know? Why? What happened? Yes, the rotation of the Earth. So the Earth has rotated. So if the Earth wasn't rotating, and that would be a nightmare if the Earth stopped rotating. Okay, so if the spacecraft goes around once, and this orbits around, takes 90 minutes. After 90 minutes, the Earth has moved some, so these points do not connect. So that's why if we were to look at more and more ground tracks, this thing will just you'll see lines all over the place. That's one example. This is a circular orbit. They don't look so insane. But if we have a inclined orbit, it looks kind of insane. So here's an inclined orbit. Look at that, that's crazy. So this is just another example, okay? So this example has eccentricity of 0.3. So it's not circular. No, it's not 0.3. It's eccentricity of like 0.63. It's got a perigee altitude of 500 kilometers. That's closest approach to Earth, and then an apogee altitude of something huge, 24,000 kilometers, and an inclination of 26 degrees. This is called, what was this? I think it was designed by the students at the Air Force Academy. It's called the Falcon Gold satellite. Yeah, right. I think their mascot is the Falcons. So it's got this crazy looking ground track. Anyway, so this would sort of lead into, if you're working for someone, right, and the customer wants coverage over a certain part of the Earth, then that's going to determine the design of the spacecraft orbit. So if you said, hey, I want to linger over, I want to have my ground track go over Indonesia and Australia, and then go by Mexico and South America. Well, here's one that does that. There's some famous ones that were used in the Cold War, where there was one that it would linger over Russia, and then it would linger over the United States. So it would be collecting things, the Molniya orbit. Anyway, this is just to give you an idea. So that's the ground. These are ground tracks. I think there's even a website you can go to see all these if you want. Go to the stk.com website. There's also something called Win Orbit. But anyway.
Professor?
Yeah.
Sorry, quick question for the IAA, the Instantaneous Access Area. When you're saying C, that refers to like what's mathematically possible, like what it could have line of sight to on the Earth, not necessarily like what its actual sensors can see, right?
Correct. It just has access to it.
Okay.
Yeah. Anything beyond the horizon, it doesn't even have access to. All right, so I'm going to say more now about the swath width and the geometry. Swath width of the instantaneous access area. So this is a schematic, but then it more clearly shows what we mean by the instantaneous access area and everything. So this is the spacecraft orbit, right? It's an orbit. It's going around. Here's the location of the spacecraft. I'll put that in red. And then this cone, this doesn't show it quite right because it's not clear that this cone is tangent to the Earth, but this is the IAA in here. And the swath width would be like the width of that instantaneous access area as we're going around. And it's as I said before, it's written in terms of either the angle or linear distance. So an angle, we might say it could see 30 degrees. Often though, people want to think in terms of what's the actual distance along the ground, and not straight line distance, right? The Earth is curved. So the distance along the ground could be 1,000 kilometers, 2,000 kilometers. And of course, that'll depend with the height. If we look more carefully at the geometry of Earth viewing, and we're going to take a slice through the orbital plane. So I'm going to draw as best I can a circle. This is a circle of the Earth. Here is the satellite. So this view is a slice. It's more of a schematic slice through the orbital plane. Here's the center of the Earth. So this is the Earth. The straight line between the satellite and the center of the Earth, right, gives us this point here, the SSP, sub-satellite point. And right? So it's like we're taking a cross section through the cone that will give us this instantaneous access area. So let me draw this kind of, I don't like doing that. Okay, there we go. So this is a perpendicular. I'm only going to draw one side of the cone. This distance here is the radius of the Earth. This is the radius of the Earth as well. And this distance is the height of the satellite, the altitude. All right, H is the altitude of satellite, instantaneous altitude. R sub Earth, the radius of the Earth. Quickly, without looking it up, what is the radius of the Earth? Nobody knows?
6,300 kilometers.
More precise.
6,378 kilometers.
There we go. You must memorize that. No, I don't know. And you're like, is that really the radius of the Earth? I thought there were mountains. It's the average radius of the Earth. It's what we're going to use, even though, yes, I know there's mountains. All right. So radius of the Earth. Often you want to know, right? Here is the red dot I will call the target. It's a point on the Earth, and you want to know if you can see it. Okay. So for the geometry written here, we write the angle from the direction to the satellite to this sort of the horizon. We're going to call that lambda naught. The angle from the direction of the satellite and the target, we'll call that lambda. So of course we can't see anything for lambda greater than lambda naught. So we'd like to know what lambda naught is. That's going to be important for knowing what is our instantaneous access area. And at this point, we also define the target point. There's the angle from the satellite to the target. We will call that this angle eta. That's the weird Greek n, eta. And this angle, if you're on the surface of the Earth, the tangent to the Earth compared to the satellite we'll call that epsilon. So epsilon is called the grazing, or sometimes called the elevation angle. And it's going to be between 0 and 90 degrees. Eta, so from the satellite's point of view, there's looking straight down, there's the nadir, and then if it's looking at the target, it would have to be at an angle of eta away from the nadir pointing. That's called the nadir angle, because it's the angle with respect to the nadir. All right, nadir would be looking straight down. And it's only 5 minutes left. I'm going to just kind of give you some formulas for how these things are all related. The maximum nadir angle is this angle from the dashed line up to here. This angle is called rho. So this nadir angle is going to be less than or equal to rho. And you can figure out from geometry that sine rho equals cosine lambda naught And sine is, right, remember SOHCAHTOA? Sine is opposite over hypotenuse. So this is r radius of the Earth divided by radius of the Earth plus h. Okay. Now the target and the satellite, at least the satellite SSP. So target and SSP each have a latitude, which will represent by delta, and a longitude, right? This lat long for points on the Earth. We'll use longitude, we'll write that as L. So the target will have a, we'll call it delta T, LT, the satellite delta S, LS. And there is a relationship between cosine lambda and latitude and longitude. And I'm not going to derive it, I'm just going to write it. Cosine LS minus LT plus, like, what is this all about? This is, if you want to know if a target point on the Earth is within the instantaneous axis area, then you need to be able to calculate these things. I guess there's another thing I should mention. The distance to the target, maybe I'll put that in yellow. The distance to the target, we'll call that D. So D is going to be, the distance to the target is going to be greater than or equal to H, right? If something is right below you on the surface of the Earth, then it's H. And then if you're away from that, it'll be something greater than that. Distance to target, like straight line distance, is r Earth, so radius of the Earth, sine lambda divided by sine eta, the nadir angle, which again comes from geometry. You're like, well, what do I get? How do I get eta? So maybe I'll kind of label these. This is 1, this is 2, here's another 3. Tangent of eta equals sine lambda, sorry, sine rho, sine lambda divided by 1 minus sine rho cosine lambda. There's another thing, eta plus lambda plus epsilon. So if you wanted to get the elevation angle, turns out those are all, the sum of those is equal to 90 degrees. So if you know 2 of them, then you get the third, and it can be proved. Okay. What about the instantaneous access area? So the IAA equals, that's a constant, Ka times 1 minus cosine lambda naught. So if we, let me quickly show, here's the Earth. It's a satellite. And this could be represented in terms of angle, or usually we want square miles. So Ka is the maximum viewing, which is actually 2 pi, right? The surface area of a sphere is 4 pi r squared. The surface area of a hemisphere is 2 pi r squared, which is something ridiculous, like 2.55 times 10 to the 8 kilometers squared. Okay, and we wrote above what cosine lambda naught is, so you could calculate what this is. So For example, for the space shuttle, let's say let's use H as 300 kilometers. And given the radius of the Earth, lambda naught is about 17 degrees. So the instantaneous access area is, about 11 million kilometers squared. It's a lot of kilometers squared. So if we were to see that on a, this is the last figure and I'll let you go. The ground track, this is actually for a different example. Here's a ground track projected on a pretty looking Earth. This is for a satellite circular orbit, right? With so this is the IAA along a ground track for one orbit. It's an orbit with H is 500 kilometers, and the inclination, well, I guess you could tell me. It looks like 45 to me, so I'll say inclination of 45. And I think you're right about the earlier one. So that's an example of, that's everything that could be seen, technically, within the range of sensors accessible. All right, we'll stop there. So that's it.